Welcome to Beyond the Brackets. This lesson is a continuation of non-exact differential equations, specifically type 3. In type 1, we discussed homogeneous non-exact differential equations. In type 2, we studied non-exact differential equations in which the entire term of dx is multiplied by y and the entire term of dy is multiplied by x. Here comes the first question. After calling it as equation 1, we observe that it is of the form m dx plus n dy is equal to 0, where the coefficient of dx is taken as m and coefficient of dy is taken as n. To verify the exactness, differentiate m partially with respect to y. So the differentiation of minus y square will be minus 2y. Differentiating n partially with respect to x, differentiation of 2xy will be 2y. Since both the values are unequal, the given equation is non-exact. If you look at the question carefully, the first term has a degree of 1 plus 1 is equal to 2. The second term x square is of degree 2. The third term y square is also of degree 2. However, the last term is a constant, which means it is of degree 0. This rules out the possibility of the equation being homogeneous. Next, if we check for type 2, we can see that although the entire term of dy is multiplied by x, the entire term of dx is not multiplied by y. Therefore, this equation cannot be classified as type 2 either. Hence, this question can be solved using type 3 or type 4 methods. To conclude which method should be used, let's do a small rough calculation. When we subtract these two terms, minus 2y is equal to minus 4y. However, when we divide this term by n, we notice that 4y and 2y cancel out, leaving a term purely in terms of x. Hence, the given equation is non-exact differential equation of this form. Substituting the values, we get f of x is equal to minus 2 by x. For type 3 non-exact differential equations, the integrating factor is given by e power integral f of x dx. Here f of x is minus 2 by x. Further, integration of 1 by x will be log x. Since a log b can be written as log b power a, minus 2 log x can be written as log x power minus 2. Also, since e power log x is same as x, so e power log of x power minus 2 will be x power minus 2, that is 1 by x square. Multiplying equation 1 by this integrating factor makes the given equation exact. The new equation obtained will be referred to as equation 2. The new coefficient of dx is m1, which is equal to minus 1 minus y square by x square minus 1 by x square. New coefficient of dy is denoted as n1, which is 2y by x. To verify the exactness, we differentiate m1 partially with respect to y. Differentiation of minus 1 will be 0. Minus 1 by x square is constant. Differentiation of y square will be 2y and differentiation of minus 1 by x square will be 0. Differentiating n1 partially with respect to x, 2y is constant. Differentiation of 1 by x is minus 1 by x square. Clearly, both the values are equal, which means equation 2 is exact. Solution is given by integral m1 dx treating y as constant plus integral n1 dy considering the terms free from x is equal to c. Substituting m1 in the first integral, for the second integral we observe that there is no term that is free from x, so integral 2 will become 0. Integrating the first integral with respect to x, integral of minus 1 will be minus x, minus y square is constant, integration of x power minus 2 will be minus 1 by x. Simplifying this further by taking x as the LCM, this is the answer. Moving on, we start by calling the given equation as 1. Again, equation 1 is of the form m dx plus n dy is equal to 0. To verify the exactness, we differentiate m partially with respect to y. The first term is not having y, so its differentiation will be 0. For the second term, 2mx is constant. Differentiation of y square will be 2y. Differentiating n partially with respect to x, 2my is constant. Differentiation of x square will be 2x. Both the values are unequal, so this equation is non-exact. Again, to conclude what type this equation belongs to, let's do a small rough calculation. Subtracting these two terms, we get minus 4mxy minus 4mxy, which is minus 8mxy. Dividing this by m will further complicate, whereas dividing this by n will cancel out the values in the numerator and denominator, and we are left with a term that is purely in terms of x. Hence, the given differential equation is non-exact of type 3. Substituting the values, we get minus 4 by x as f of x. Again, for type 3, integrating factor is given by e power integral f of x dx. Integration of 1 by x will be log x. Further, minus 4 log x can be written as log x power minus 4, and e power log x power minus 4 becomes x power minus 4. So the integrating factor is 1 by x power minus 4. Multiplying equation 1 with this integrating factor, we call this equation as equation 2, wherein the coefficient of dx is m1 and the coefficient of dy is n1. Further, to verify the exactness, differentiating m1 partially with respect to y, differentiation of e power x will be 0. 2 minus 2m by x cube will be constant, differentiation of y square will be 2y. Differentiating n1 partially with respect to x, 2my will be constant, differentiation of 1 by x square will be minus 2 by x cube. Both the values are equal, so equation 2 is exact. Solution is given by integral m1 dx treating y as constant plus integral n1 dy considering the terms free from x is equal to c. Substituting m1 in the first integral, we observe that there is no term in n1 that is free from x, so second integral becomes 0. Integrating the first integral with respect to x, we get integration of e power x as e power x minus 2my square will be constant, integration of x power minus 3 will be minus 1 by 2x square, which brings us to the end of this question. Let's quickly move on to the last question. Once again, we call the given equation as equation 1, which is of the form m dx plus n dy is equal to 0. The coefficient of dx will be m and the coefficient of dy will be n. To verify the exactness, differentiate m partially with respect to y. Differentiation of 3y square will be 6y. Differentiation of 4xy will be 4x. Differentiating n partially with respect to x, differentiation of x square will be 2x and differentiation of 2xy will be 2y. Again, both the values are unequal, so the given equation is non-exact. To determine the type, let's do a small rough calculation. On subtracting these two terms, we get 6y plus 4x minus 2x minus 2y, which gives 2x plus 4y. Here 2 is common in both the terms, so we get 2 into x plus 2y. Dividing this term with n, x plus y will cancel out in the numerator and the denominator, and we are left with a term that is purely in terms of x. Hence the given equation is non-exact differential equation of type 3. Substituting the values, we get 2 by x as f of x. Integrating factor is e power integration of f of x dx. Integration of 1 by x is log x, and 2 log x can be written as log x square. E power log x square is equal to x square. Multiplying equation 1 with this integrating factor to obtain a new equation which will be called as equation 2. Coefficient of dx will be m1 here and coefficient of dy will be n1. To verify the exactness, differentiating m1 partially with respect to y, we get 6x square y plus 4x cube. Differentiating n1 partially with respect to x, we get 4x cube plus 6x square. Again, both the values are equal, which makes equation 2 exact. Solution is given by integral m1 dx treating y as constant plus integral n1 dy considering the terms free from x is equal to c. Substituting the values of m1 in the first integral, for the second integral we observe that there is no term that is free from x, so second integral becomes 0. Creating the first integral with respect to x, for the first term 3y square is constant, integration of x square will be x cube by 3. The second term 4y will be constant, integration of x cube will be x power 4 by 4. The third term integration of x cube will be x power 4 by 4. With this we conclude this topic. I have included a few additional problems for you to practice along with their answers.